Okay, I would like to take a minute to talk about acceleration graphs and the graphs that you're going to be responsible for knowing what's happening in. So, first of all, we have basic acceleration and time. And if acceleration is constant, it should look like a straight line there. All right? The next graph is the velocity versus time graph. And if you've got a velocity versus time graph, if the acceleration is constant, the velocity versus time graph will look like that. It'll be constantly increasing. Okay? Then, the next one, distance versus time, it will look like a parabola. Alright, so this is if acceleration is constant and positive. But what if acceleration is negative, alright? What if we have acceleration and time and acceleration is down here, okay? So what if this is the line? I'm going to do this in a different color. What if that's the line? Well, in that case, what we have is a graph that looks like this. Velocity, time, and the velocity graph will be going down, exact opposite of the one above. And then the last thing is, what about the distance versus time? Well, the distance versus time will be a reflection, basically, of what it looks like up there. So essentially that. Now that's if acceleration is negative. Okay? And we're also assuming that we start from a velocity of 0 and a distance of 0. Okay? So what about if we have a velocity versus time graph and it looks like this? What is acceleration doing? Well, acceleration would have to be a negative number. Alright? And the distance versus time graph for this would look something like this. Because as it would be fast, or you'd be increasing your distance per unit of time faster at the beginning than you would at the end, and then toward the end it would start to taper off. Okay? What about this graph? If we had velocity versus time, and we had a graph that looks like this. Well, this is interesting because this would be two different graphs for two different things. If we had distance versus time, I'm going to draw a line to indicate these are two different things. Distance versus time would look something like this, where you were speeding up initially, where you're slowing down initially, but then once you get past this point right here, you would start to speed back up. Alright? So you slow down until you get to a certain point, and then you speed up. The displacement versus time graph would look a lot different because displacement cares whether you're going positive or negative. So if we were doing displacement versus time, the displacement versus time graph, since it's concerned with your position, would look a little different. And in this case, we would start up here, and we would be going back, we would be starting here, and we'd be going slowly up to a point. And then once we reach this point, alright, we would start to speed up, but it would be in the negative direction. So we'd be going back to the starting point. So the critical thing to note here is that at this point, you start going backwards. Alright? So those are the different graphs. These may not come up on the test. I'm just showing you what they look like so that if you see them ever, you've been exposed to them and you know what's going on. Alright, there are a multitude of graphs I can show you. The last thing I'm going to show you, though, is just to make sure we all remember this. If you have a velocity versus time graph, and you have a line segment drawn like this, and it asks for the distance traveled, all you need to do in order to find this is to find the area under this curve. Okay? It's important to note it's the area between the line and the 0 point on the y-axis. And so the reason that's important is, hang on, let me try this. Distance is equal to the area. Let me show you why that's important. what if instead of a graph where the velocity is always positive, what if you had a graph where velocity was negative? Okay, so our velocity was positive and negative. So it starts off here and it goes down. Let me just erase that. Alright, so it starts here and it goes down. Well, now, wherever this 0 point for the velocity is, it might be here. You need to check because it's not always going to be drawn. But wherever that 0 point is for velocity is the line that you need to draw. And you find the area between your velocity slope and that 0 line. And that area is your distance traveled. Okay? And the last thing we need to talk about is if you're looking for the average velocity, or sorry, rather, the average acceleration, that's equal to the change in velocity over the change in time. So let's just say that this is 0.3 seconds and this is 0 seconds, okay, and this is 6 seconds, okay. The acceleration should be the same throughout, right? Because it's got the same slope. So if I wanted you to find the acceleration from 0 to 3 seconds, you would just find the change in velocity from 0 to 3 seconds, alright? You just plug it in and you could solve for it. Alright? That's how you find average acceleration on a graph. Alright, hopefully this makes sense. If it does not make sense, feel free to email me. You may need to watch it again. I realize this is probably not the most exciting of videos, so you may not want to watch it again. But if you have any questions over this, it is a fairly important part. It's important to know how to read the graphs, so feel free to let me know.